My pleasure to introduce our colloquium speaker, Dr. Sara Hornby. She is currently the president of Global Strategic Solutions at North Carolina, United States. She is the first woman to graduate from Sheffield Hallam University, and later she completed her PhD in industrial metallurgy. She spent her early career days working in UK industries, which includes British Steel Corporation, and later she moved to United States and Canada and worked in metal industries, managing multidiscipline, multi-location team members coupled with electric arc furnace steel making optimization, which actually puts her in a position to start up her own consultancy company called Global Strategic Solutions. Dr. Hornby hold almost 5 patents till today and authored 136 international papers, which include seminars, courses, etc. She is a fellow of IOM3 and also the recipient of Hadfield Medal in 2022. In addition to that, she is also the recipient of Benjamin Fairless Award and John Bell Award. In 2023, she was awarded an honorary doctorate degree in engineering by Sheffield Hallam University. Today, she is going to deliver a talk on green steel revolution. Sarah, thank you so much for your valuable time. And also, I would like to tell our audience that today is Sarah's birthday, and I wish you a very, very happy birthday. And
Thank
floor
you
is
very
yours.
much.
Thank you.
Thank you, Prakash. And welcome to all. Thank you for inviting me to the colloquium. Apologies for my voice. I'm suffering major allergy reactions in North Carolina at the moment. So the Green Steel Revolution. This lectureship is sponsored by the AIST and TMS Lectureship Award. It was established in 1990 to honor John Frank Elliott. He was a late professor from MIT and has many significant pyro and chemical process metallurgy contributions. The idea is to acquaint students, engineers, and even the public with chemical process metallurgy and its contributions and the exciting opportunities that are there for students within the career field. Excuse me, in 1972, he wrote a paper, 100 Years of Progress in Process Metallurgy. And in fact, at that time, he said electricity would become more important as an energy source than it is now. But he was probably not considering CO2 and hydrogen at the time. Now, I'm honored to have been chosen the 2024 Elliott Lecturer. And a fun fact for the students that might be challenged by their choices and their degrees currently, I failed my chemistry at A level and almost failed my Chem Met. And I have spent 50 plus years in the industry. So if you have a burning desire, anything is possible. So why the Green Steel Revolution? My definition is zero emissions steel making using fossil-free energy sources. And of course, the zero emissions iron making is the most crucial for the greenhouse gases, as I will show you. But at this point in time, it's not cost competitive with fossil-based. But currently, as you can see from the chart on the right, we're not at the 1.5 degrees C global warming target. And in fact, we increased CO2 emissions or CO2 equivalent emissions in 2021 and again in 2024 to 37.4 gigatons of CO2, which is an 8.8% increase. So why the Green Steel Revolution? In 2015, the plan was to convert 800-year-old blast furnace BOF technology to the 60-year-old EAF technology and make some major changes in the modus operandi there. So carbon-free electricity, green carbon and consumables, and hydrogen direct reduced iron as a charge material. But as everyone's seen, there's increasing disinterest or inability to comply with this solution. And it's motivating out-of-the-box thinking and new iron and steel making research. But it's valuable to note that in 1980 through 90, there was a lot of work done on this with little success. I'm not going through these, but just to demonstrate blast furnace smelting, reduction, direct reduction, and scrap recycling. At the bottom, there are the figures for the iron making and steel making. And as you go from left to right, you're going from 2.2 tons of CO2 per ton of hot metal down to 0.38 for 100% scrap recycling. Chart at the top just shows how the different processes for steelmaking has taken over the years. Carbon dependence in both the processes shown here. I'm not going through all the calculations, but obviously with the blast furnace, currently there's no opportunity to completely replace the coke used. In the electric furnace, we have carbon used for chemical energy and foamy slag reactions. And of course, foamy slag has become very significant in processing over the years because of the reduction in heat loss, increased chemical activity, and the yield and productivity effects from it. The CO2 equivalent sources, the right-hand side shows in the table that the blast furnace obviously is the biggest emitter, followed by the sinter EAFs are the third largest. The Paris Accord is requiring that we have 0.2 tons of CO2 per ton of steel by 2050. Right now, we're at an average of about 1.7. Major emissions, as I said, are from the blast furnace. And the chart down below actually separates out the countries that produce more than 10 million tons of steel a year. And it's coded by blast furnace BOF in the red, and green is the EAF steelmaking. And you can, as we all know, China is making about 54% of the steel in the world. Back in 2021, it's not changed much since. And that's contributing to their 28% emissions. And India is the second largest at 57% EAF steelmaking. And strangely enough, the USA is one of the largest emitters, but not specifically from the steel industry, because we are about 74%, excuse me, EAF steelmaking now. Fun fact, Canadian fires were the fourth largest emitter in 2023, emitting 647 million tons of CO2. So if we look at the International Energy Authority's vision and green challenges, of which there are 9, technically the 95% hydrogen DRI EAFs they expect to have online by 2070 are technically feasible, but there are major challenges which I will go through. There's like 9 of them. And these will, the challenges are promoting research, which are from lab scale TRL3 up to demonstration plants at 7, some of which have become viable in less than 3 years or 4 years. It is the most exciting era since the 60s when continuous casting was developed. And the first of the 9 challenges is what I call the build rates. I believe they're unreachable. The future is predicated on the ability of hydrogen, energy, carbon, and better qualified scrap being available. And if you look at the numbers, in the 50 years that DRI began, there was only 2 million tons a year of DRI plants built as an average. By 2050, IEA is projecting we'll need 411 million tons of DRI, of which 213 million will be hydrogen-based. And that's going to require 11.5 million tons of hydrogen per year, 692 terawatts, and 1,240 20-megawatt PEMs, and 810 electric arc furnaces. And that's an enormous number of plants to be built to comply. Additional to that, as I will show you, zero carbon DRI that's produced with the hydrogen, even if you look at the 80-20 running of DRI with natural gas, hydrogen and natural gas, is going to require 370 additional terawatts for melting. And we've got now supply chain challenges, which have occurred since COVID. Transformer deliveries are 106 weeks, for example, and some of the costs are 85 to 100% now. The second challenge, of course, is sourcing the green hydrogen. It's expensive. There's an inadequate supply. The Lindy Gases has put together some numbers on the right-hand side. I won't go through them, but they're there for your edification. And in 2023, for example, 45 million tons of greenhouse gas projects were announced. $570 billion worth of investments. And the chart below is from the hydrogenmap.com. It shows that in 2023, there were 1,040 projects, $110 billion in front-end engineering and development, and only 25% passed the front-end final investment decision, with 7% of the investment. Another issue with hydrogen is the production efficiency. Currently, the processes that are out there are between 27 and 65% more energy required than the basic 39 kilowatts for kilogram of hydrogen. There are some projects ongoing. There's a plasmalysis jet loop ammonia stripping process that's saying they will be able to do 8 kilowatts per kilogram, and they're taking that from wastewater and manure. There's a next process in Australia with RMIT, and they're integrating sound waves with the nominal and existing electrolyzer processes and getting 14 times the production rate. And there's another company called Utility that's got H2Gen, and their hydrogen production is coming from using water, but they're using a blast furnace gases as the hot rather than electrical energy. They're using it as an electrochemical heat source to allow the hydrogen production. And they're able to concentrate the CO2 more efficiently for use elsewhere. The other issue is CapEx. Promises were $300 to $500 per kilowatt. However, they're closer to $1,750 right now. The third source problem is sourcing the renewable energy. The right-hand chart shows the different renewable energy sources or energy sources that exist in the world. There's very few renewables. We need 1,437 terawatts because the steel is basically taking 8% of the world energy, and CO2 emissions, depending on the source, are between 0.3 and 1 kilogram of CO2 per kilowatt. The chart has come from the globalenergymonitor.org. We basically have not enough energy, renewable energy at the right price. We need a drop of at least 50%, and even more in some areas in the world. Renewable energy in 2022 was 29%, which was an increase of only 1% over 23. China is leading the way. Capacity adds in 2023 were 0.5 terawatt and 0.6 in 2024. And if you look at energy use being 67% efficient, to produce 500 million tons of hydrogen is going to need 19% of the total world energy requirements. Hydrogen was anticipated to be an energy source in general for the future, but now only 2 to 3% is going to be used by 2050. And one of the big issues that we have is we have not anticipated the need of water that we're going to require for the future, and it's anticipated we will be 30% in the hole moving forward. Challenge number 4 is sourcing carbon. Historically, we produced iron by a renewable process, but in the 20th century we went to electricity and coal, but when the OPEX became 20%, energy became 20% of the OPEX, it forced minimization. There's some numbers there of how the best run furnaces and systems operate. Biomass use, which is shown in the top right-hand graph, varies by location. Brazil is obviously the one that's furthest ahead in the world, and I believe 88% of their energy is renewable. The surprising factor was that the US is close to Brazil, and I'm not sure where they are using all the biomass that they say is being used. The cost of processing reduces the world opportunities. And the other question is whether there's enough sustainable biomass that's close to the potential use points that would match the use rate required. Obviously, blast furnace coke currently can't be replaced because they need it for bed support. Kobe Steel has the record at 239 kilograms of per ton of hot metal. And one of the other issues is replacing the carbon in an EAF. Currently, the average is about 50% of efficient, and I'm saying efficiency by combustion definition. If you're injecting, it's 50%. If you have it as an in situ carbon in either pig iron or DRI, it's 95% or more. Excuse me, the fifth sourcing challenge is scrap. For the 100% scrap EAFs, it's the lowest emissions, especially if you put renewable energy on. It drops it to about 0.18 tons of CO2 per ton. But most of the quality issues with the steel trace back to the melt shop, and that's partly because of the lack of specific quality to which the scrap is sold. And as we know, prime is dwindling. Obsolete glut looms because China is predicted to put 40 to 500 million tons a year of scrap into the market within the next 10 to 20 years. And the continuous recycling is going to increase the issue that we have with copper and trace elements in the scrap as we move forward. So it's becoming a big issue. The sixth challenge is the zero carbon hydrogen DRI in the EAF. You can see from the top chart that only 55% in this particular case has come from electricity. In terms of energy, 23% is coming from carbon oxidation. Carbon, as I said earlier, promotes the foamy slag. And with that comes stirring of the melt, increased heat transfer. And the carbon in the DRI currently reduces the FeO, both in the DRI and in the slag. And it also has the benefit of no ash, no volatiles. The chart on the bottom right, excuse me, is something that our friends at ArcelorMittal put together for benefit of carbon in their DRI. And they said for every 1% of carbon that they had in the DRI, they reduced their kilowatt hours in the furnace by 25 max. Electrodes are down 1.5 kilograms. The production can be up as high as 1.5% increase, and the yield is up to 1%. If we have zero carbon in the DRI or inefficient carbon use, we're going to end up with increased cost and lower productivity because there's going to be more gain in the system. We're going to have higher kilowatts, higher meltdown and tap times, higher refractory and electrode wear, lower yield, higher temperature and melt with the lower carbons, be more FeO in the slag. Biomass carbon needs fossil co-injection currently to operate correctly, although there is a new process that's supposed to be 98% efficient with injection, but the fineness of the carbon replacement is causing plugging in the equipment currently. But if we have all these scenarios, especially with a higher slag volume involved to give us the quality of liquid steel, we're going to have to redesign the EAF and the refractories to compensate from that, to prevent carbon dissolution from the refractories. And we're going to have a deeper bath. It's going to have to be stirred either electromagnetically or physically. We're going to have more slag formers required and more slag to dispose of, and therefore more cost. And all of this is going to be compounded by the lack of or dearth of DRI grade ore. Sorry, my computer's decided to lock. So the seventh challenge is sourcing the DRI grade ore. And by that, I mean the DRI plants can basically handle any of the ore that's thrown at it. But to process that DRI in an EAF, we need to have more than 67% iron containing ore. The quality of the ore around the world is deteriorating. We're already seeing a 2% drop in iron content. Silica and alumina are increasing by 2%, and the phosphorus increased by about 0.02%. 35% of the ore comes from Australia, and the Pilbara ores that they have there are difficult and costly to upgrade. They're doing a lot of work on it. But currently the thought process is, and not just for Pilbara, but with the lower grade, weaker ores, that we redirect the DRI into a melter, so a submerged arc furnace, basically an ESF, and then put it to a BOF or an EAF as hot metal or as pig iron. There's new technology for the lower grade ores. Electra is producing iron from 30 to 35% iron containing ores at 60 degrees centigrade, and that's being sponsored by Nucor. There's a process out of Australia I'll go into a little bit more later, which is producing DRI with hydrogen from fines. And Swinburne University in Australia, along with CSIRO, are working on this highly reducible flux lime magnetite pellet, and that's allowing the process to be basically constrained a little bit, and two process steps are being removed. That's the left-hand lower chart that shows the processing current and the processing potential. On the right-hand side is the chart put together by Prime Metals that basically shows that 67.5% is what's required for the processing of DRI through an EAF. I think that's a little bit on the high side, but the lighter colors there are the transformation costs, and the darker colors are, the blue is the DRI, and the lighter colors are basically the transformation costs that you've got. And then the DRI costs are the darker ones below. Number 8 challenge is the availability of carbon capture use or storage. It's substantially below net zero requirements currently, and yes, it can. It can address the 54% of the hard to abate emissions, but currently 35 plants in the world only capture 45 million tons of CO2, which is 0.12% of the world's requirements. And the new CCUs that were announced last year that should be operating by 2030 only increased that 0.6%. The chart on the right is from the IEA.org, and it basically shows that very little of the CCU capacity is looking at the metals industry, basically. Relatively high cost of conversion because you need carbon-free hydrogen in order to chemically stabilize the CO2, and fixation is limited. And sequestration, of course, is geographically challenged around the world. And also it's temporary if no mineralization occurs. So whilst they've been slated as a catch-all for solutions, there was an interesting article last year from Sandbag that says basically CCUs don't make sense economically, environmentally, or energy speaking. And they said that the effectiveness and relevance basically varies depending on the application. And they were suggesting it would be more appropriate for the Europeans that they were referring to look at the direct reduction plants and other solutions rather than spending money on CCU research. Now, Baotao, Steel in China is putting in the first commercial one, supposedly at end of fourth quarter. It was 500,000 tons, moving to 2 million tons ultimately. I haven't found the status of that yet. The other problem is the end users. Currently, food, chemical, and enhanced oil recovery. However, can they truly use all of the CO2 we might be able to catch? Back in the late 80s, early 90s, I was doing a lot of work using CO2 in the steel mills as an inert gas, funnily enough. And I suggested back then it was possible to capture the CO2 and use it in lieu of argon and nitrogen for the majority of the applications. At that time, it was too expensive, so I'm hoping now that the gas companies are looking into this. Challenge number 9 is the cost, conversion costs. It's truly uneconomical unless there are significant government subsidies. The 60 EU projects shown on the map here are $92 billion worth of money financing. DRI costs double using green hydrogen, and steel cost triples, or will triple by 2030. So we're already non-competitive as the Western versus the Asian producers. The numbers here were taken from May last year, but the USA was producing hot band at 839, Western Europe at 680. The world export number was 580 and China was at 448. So it's necessary, of course, to levy border and import or black steel taxes to non-compliant nations as we move forward. And basically, the predicted carbon tax in Europe, unfortunately, is stipulating that financially the carbon tax needs to be over $300 per ton before it becomes financially viable to consider moving forward with a huge green steel conversion. Projects are faltering. The final investment decisions are negative in a lot of cases. I think basically because there's no short-term gratification. Costs are rising. There's some projects there that are listed that are delayed, and we all know that ArcelorMittal has delayed a lot of their projects by up to 10 years. Some of them have already been cancelled, and I'll show you a little bit later that the number of blast furnace operations are increasing significantly. So my thought is that we need to look at revamping blast furnace BOF process and work on the ability to upgrade that as we move forward. So new technology developments, basically looking at biomass, CCUs, hydrogen reduction and production, electricity, and I've set up scaling what we call non-steel old technologies such as the SAF and the OSPFs. There are 3 processes in the world running with iron and steel making, iron making, none of which are, I believe, running to full efficiency or capacity. Challenges for everything appear to be increased energy, scalability, timeliness to market, and the Chinese techno-economic advantages. So again, best available technology and more AR&D at brownfield sites really should be a must moving forward as a stopgap. Timely solutions, this is just an example I put out here. The blue area was the claim a few months ago saying we've developed Phoenix in 15 years. Well, if you look at the data, it's actually more than 80 years since they started working on that. And the second example I've got in here is Hisarna. This is a 38-year development of the cyclone converter with a smelt reduction furnace. Research is still going on. So some of the new technologies, excuse me, electric smelting furnace is predicted to be capable of taking the excess lean ores and the unsuitable DRI. However, they need to upscale it. Currently, they're 1.1 and 1.4 million tons a year, whether they're circular or rectangular. But they need to optimize power intensity, sustainable renewable energy use, and the electrodes, which are currently carbon, and integration of that into a normal plant, large plant, won't be a problem. BlueScope, BHP, and Rio Tinto are working on an ESF for the Pilbara ores. Currently looking at the project. It's been announced, but they're doing the studies currently. And it should be noted, BlueScope's also relining their blast furnace. Rio Tinto has also got a bio-iron project ongoing, which is using microwaves. And Gravit HY is using IOC ores, or will be using IOC ores in France. And the agreement is that Rio Tinto will be marketing all the HBI that they produce. Fortescue, Prime Metals, and voestalpine was supposed to be developing the prototype HYFOR. Fortescue has just pulled out of that process. And I believe that they've been replaced by BlueScope and potentially Rio. And they've got a 1 ton an hour plant that's been running, excuse me, since 2016. And the 6 ton an hour demonstration plant will be put into Linz in Austria by 2027. The decision is going to be made fairly soon. It's been delayed since 2024. The other is POSCO's fluidized bed Hyrex. It's a hot hydrogen ore reduction and an ESF DRI melting furnace. They think they'll have a 300,000 ton a year demonstration plant in by 2028, and that they will have a commercial plant up and running by 2030. The biomass zero iron making, as I already said, it's dependent on where you are in the world. Brazil is the largest biomass and iron ore producer, using 88% renewable energy and charcoal in their blast furnaces. It's, again, a situation where you have to match availability with the requirements. And one of the big questions that's come up recently is the emissions life cycle analysis, whether having land used changed for harvesting and producing of charcoal versus crops, is it economically viable? Also, the question becomes, is carbon neutrality actually achievable? Now, Red Smelt in Brazil is claiming that they can achieve the zero emissions with a rotary hearth furnace and a submerged reactor. Ferrosilva in Sweden is claiming that they can actually produce a sink of CO2, 0.845 tons, and they're going to make it using syngas derived from forestry and agricultural waste. They're going to send biochar to the steel mill, and they're going to capture the CO2 potentially for fossil-free ship fuel and biomethanol production. So they're currently in the pre-study phase, and they're looking at a 50,000 ton a year DRI plant in Ovako, High-Fors in Sweden. And the process diagram is at the bottom right-hand side there. Solid DRI process, Calix is a new Australian company that's actually, it says 2.5, but it's 3.5 years now since inception. They've proven the ability to produce green iron from the Pilbara ores. Metallization is anywhere up to 98%, but not with all of the ores yet. They're using green hydrogen on they're two concentric tubes, basically. Green hydrogen on the inside tube with the countercurrent to the ore fines, and renewable energy in the outside column. They're getting close to stoichiometric hydrogen use. They're doing an ARENA study, or requesting an ARENA study right now, for a 30,000 ton a year plant, where they will actually increase the height of the tubes to give them longer residence time for the more lean ores that will technically reach the 90+% metallization. And they have a process ongoing with their zero CO2 lime process, which is how this all started. They were producing zero CO2 lime. And they will combine all of that to put the zesty steel process together. Amazingly, the solid DRI processes only show TRL 6 to 8. I'm assuming it's because of the hybrid hydrogen process, and also the open question of whether we should maintain carbon in the DRI or not. Hybrid, of course, has run at a ton an hour of DRI with full hydrogen. They've proved this lined rock storage that they require for the hydrogen to function. And they've proved 100 cubic meters, and they'll need 120,000 cubic meters for the new plant that's going into Gallivard, which will be a 1.3 million ton a year renewable energy H2 DRI EAF steelmaking plant that should be running by next year. There's also a hydrogen rotary kiln that's running on solar and wind. There's a 0.5 ton high iron DRI plant in Germany running on 40 megawatts of renewable energy. And this high iron is going to do a joint venture with Hyron, or has actually, because they've just produced the first iron in Namibia. 15,000 ton a year to start with, running on 20 megawatts of solar. And they will ultimately meet the 2 million ton a year DRI by an additional 18 megawatts of wind and 140 megawatts of solar. Electrolytic iron making. Obviously, electrowinning can be either high temperature at 1500 degrees C or low temperature at about 110 or less. The redox reaction is iron at cathode, oxygen at the anodes, and the actual oxide anions in the ore are the reducing agents. Higher efficiency because the renewable energy is direct contact. The high temperature process dissolves the ores in the molten electrolyte, giving liquid iron. Faster kinetics, but higher capex and opex. ArcelorMittal et al. Explored this Medeo, which came from the Olcos work that was done. And they were looking at it between 2004 and 12, but I don't think it has moved forward. The low temperature solid iron process is, of course, lower energy use, and lower capex and opex, but it's a slower reaction rate. And ArcelorMittal does have their Sidewin demonstration product running, which is 110-degree aqueous process in batch to produce iron plates. The American equivalent is Boston Metals, which is high temperature. It can process a wide range of ores, but it's limited in productivity per cell because of the current density in the Faraday's law. The critical factors for them are ability to recarburize once they've got the iron, longevity of the anode and choice of the anode, and scaling. They're going to have to scale up 240 times to get commercial. They also have an issue with cell voltage. It's been running at 20 volts and it needs to be down at 5. And the question becomes, are steel mills willing to put in 400 of the cells, examples of actually aluminum cells on the right-hand side? It's 400 cells to produce 500,000 ton of steel. So if you have a 4 million ton a year steel mill plant, you're going to need 4,000 of these cells, which are all batch operated and have to have the tap holes blown. They've got a lot of DOE funding, or did have, I don't know, with the current status, whether they're going to get any more. They do have a mine processing, waste processing plant in Brazil, and they think they will have a fully operational steel process up and running by next year. Some other electrolytic processes. Electra in Texas is sponsored by Bill Gates and Amazon. It also has been up and running for less than 4 years. It's a low temperature process, and it's converting 55% iron ores to 99 plus. It's electrochemical and hydrometallurgical. It's creating 1 square meter of blocks, but we don't know how thick. And that will go straight to an electric arc furnace with virtually no tramp elements. And there's also the Olcos offshoots. I already mentioned Sidewin, that's being run by ArcelorMittal. There's Ulcowin, which is ArcelorMittal's low temperature direct alkaline electrolysis, and Ulcolsys, which is the high temperature one that's equivalent to Boston Metals. Excuse me, plasma iron making has arisen again. Basically a plasma arc electrode to the ore in a conventional furnace. It's very energetic species of hydrogen that are created, which overcomes the endothermic nature. There are enhanced kinetics and energy savings, lower reaction temperature. There's a pilot demonstration at the University of Leuven with Voestalpine cooperating. Historically, this has been overpriced for the industry and failed in the 80s and 90s. They need to find a lower capex. They need to find a new reactor design with a better efficiency than there was. And refractory life was a big issue when they originally brought this to the industry back then. There are some examples out there. There's a hydrogen plasma red in the research in Europe, which is 100 kilogram scale currently. If it works, it's going to be retrofitted to a DC arc furnace. There's a potential for the aluminum bauxite waste, which could be 180 million tons a year turned into iron-making feedstock. And I already mentioned this plasmolysis to strip ammonia from wastewater and manure. So if we look at the opportunities on the brownfield decarbonization site, blast furnaces obviously would be the prime objective. We're still looking at 50% of the world's iron coming from blast furnaces in 2050. So we need to do something about those that remain. It is the greatest potential for CO2 reduction. Improving measurements in the mill would be the start. Blast furnace pellets, we already know, reduce the CO2 by 85% compared to sinter. We need to intensify metallics use in the blast furnace, either scrap or HBI. The IIMA showed, the International Iron Metallics Association, showed an 8% productivity increase and a 7% coke reduction for every 10% metallization that was put in the blast furnace. And the US Steel actually showed this back in the 80s when they were putting metallics into the furnace. Biochar substitution, of course, for coke and pulverized coal injection. Hydrogen or methane TWIR injection. It's shown to be 115 kilograms of natural gas has basically reduced coke 9% versus coke alone. And Hatch has predicted that if you use PCI, 35 kilograms of 900-degree hydrogen, you can get 20% reduction in CO2 and an additional 35% of energy to the steel mill, but it's going to cost a lot, even though there's 100 kilograms of coke reduction. If you add to that top gas recycling and CCUs, you can potentially produce an 80% reduction in CO2, which would bring the emissions from a blast furnace down to 0.4 tons of CO2 per ton of liquid steel, which is almost as good as 100% scrap in an EAF without renewable energy. Japanese Course 50 program, of course, has shown 30% reduction already, and they're aiming for 50%, moving from hydrogen, coke oven gas, and CCUs on a 12 cubic meter diameter furnace, a small one, to blast furnace plus DRI plus hydrogen. Kobe, we've already talked about their low coke rate, and they achieved that with 20% lump, 80% self-flux dolomitic pellets, and PCI at 200 kilograms a ton. This utility H2 gen, hydrogen from water using the off gases from a blast furnace or even a BOF. They don't use energy, it's low cost, and it's a low negative carbon footprint. They've run it at Stelco and Nanticoke, which is now Cleveland Cliffs and Lake Erie. Its first commercial plant is going in at 3 tons of hydrogen a day from blast furnace gas, and the hydrogen pricing is interesting. Less than 20 tons a day of hydrogen would be less than $5 a kilogram, but if you get bigger than that, it's going to be way less than $3 per kilogram. In fact, they were talking more like 1.5 to 2, which is perfect for the industry. So BOF, again, increased scrap use would increase productivity and decrease the CO2. The two right-hand diagrams are from Swinburne University. They worked with industry and developed this program from their data. And basically, if you increase scrap, it reduces heat loss. And you can see from the top chart, if you go to 35% scrap charging, your heat loss drops to about 0.9%. And if you conversely look at the low end, which we are currently as a world, we're about 17% use, you're going to end up with 6.75 to 7% heat loss. If you, on the bottom chart, increase the post-combustion ratio from 10 to 30%, then you can increase scrap from 22 to 28%, which is the dotted line, and your global warming potential drops, which is the red line. Also, the HBI and the BOF has a greater cooling intensity than scrap does, and of course, it increases productivity. And the charts at the bottom just reiterate that. The thing to note here is that the H2 gen, if they take the off gas from the BOF, actually get a higher CO2 concentration also for use later. EAF, green energy, is the key, obviously. If you look at the top right-hand chart, moving from scrap to scrap EAF to scrap renewable energy EAF, you're going to drop about another 7 or so %, if not more, versus the blast furnace. And of course, hybrid is a little blip on the extreme right that's even lower. Beneficiating the scrap is a need. And I know that a lot of work's been done in England proving this. And we need to beneficiate the scrap to reduce the amount of ore-based metallics that we actually need. Shredding in-house, improving the quality and density and the yield, and also the profitability from the fluff from the shredder. It can be sold quite a good price. Excuse me a minute. One of the things that I think is necessary is continuous analysis of the scrap that's being charged to the arc furnaces. It's being developed, but not really being used currently. But that would help to defray some of the problems with melting. Developing residual insensitive steel grades, or take residuals out of the scrap. People are working on both those projects. Nothing significant to report yet. Using preheat on the combustion air for the burners could also benefit the industry. You can drop, this particular case that I worked on, 480 kilowatts can be dropped to 280 if you do that, and you can drop meltdown time 16 minutes. Obviously, we need to develop the green carbon and consumables for the use in the arc furnace. Hydrogen substitution, partial or fully, for the natural gas in the burners has already been worked on and is being tested in some of the plants. But also for the lowest cost liquid steel, we need to maximize our operating efficiency. And to do that, I think we need value in use programs, off-gas analysis to reduce the heat loss to the to the off-gas system. And we need EAF control. I worked in a plant last year that only had all the tools, but they only had level 1 running, and it caused a lot of issues for control. So the industry status, this is the map of all the projects in Europe, the 60 projects I mentioned. They're all color-coded. I'm not going to go through them all. A copy of the presentation will be available. But there is also a new map from Europe as of last week that shows the current status of all of these projects and how the delay is affecting some of them, which is at the back end of this project, at this PowerPoint. I will not go through it because of the length of time it would take, but I'm including that in the process. This is a great map. It's globalenergymonitor.org and by projects. It looks at all the steel mills that have more than 500,000 tons a year production in 89 countries. And it basically on the left-hand side shows the number of plants that they have, which is 1,163. And then they break down the plants on the right-hand side and color code them for the map, depending on what process you're looking at: electric oxygen, integrated blast furnace, integrated DRI, and then it drops down to the iron making, DRI, and blast furnace. And then it categorizes them by announced, construction, operating, mothballed, retired, cancelled, and operating. And if you take one of the circles that's got a number inside it and explode it, top right, it will color code all of the plants in that particular circle and explain what process it is. And if you drill down further, as I did with Soldana Steel at the bottom of Africa, you can get all the plant data, and even after you get the general plant data, you can drill down even further on each of these processes. But for time, I just summarized the tracker. And the big surprise is if you look at the A announced and C construction columns that are ongoing. 2 years ago, the integrated DRI and the iron-making DRI were way ahead of blast furnace. But now, as you can see, there are almost the same number of integrated blast furnaces and DRIs announced. And in terms of iron making, the blast furnaces come up to 15 versus 27 on the DRI plants. And in fact, on the construction side, there are more blast furnaces than iron making DRI plants going in. And the integrated plants are about equivalent. So there's been a big change recently. International solution is potentially decoupling of the iron and steel making. The solutions are going to vary by location. China's got very young blast furnaces and aren't likely to shut them all down and put electric furnaces in a hurry. Excuse me. India's got low tons of scrap, so they're going to continue with their DRI production. Their infrastructure's a little bit lacking, but they are growing significantly in tonnage. The renewable energy sources vary considerably. China's ahead in the world, of course. MENA, with their solar, they're putting in a Midrex Flex DRI in Algeria and Libya, and they're going to put in 8.1 million tons of DRI, 2.7 of which will be the first phase. And there's a lot of international alliances going on. Germany sponsoring Colombia's efforts, Rio Tinto supplying IOC pellets to Gravit HY and taking back the green iron to sell. CCU scale up, of course, as everyone's saying, is vastly overestimated for the Chinese, Indian, and South Korean deployment, which is an issue because they're the biggest polluters in the world. But this seriously needs to be thought about. Australia is doing a lot of thinking about renewable energy and how they can produce iron or HBI for sale, as opposed to selling their low-grade ores. I just put this map in to show how China has basically expanded their port capabilities around Africa. It's significant now. And there's some information there on China, India, and the US in terms of market strengths and key challenges. Projects in development in Australia are listed here. I'm not going to go through them, but there are a substantial number of projects. There's $1 billion of funding available across the country from various provinces, states. Permitted green installations, predominantly Europe, are here. Again, these are the ones that are going ahead, not the ones that were announced. So basically, in summary, the scale of progress and investment falls significantly short of the 1.5 degrees centigrade goal that's needed for the greening of the future. Hydrogen DRI EAF steelmaking is technically viable, but challenged with huge issues moving forward, the biggest of which is conversion costs. And we also have a catch-22 because suppliers of low or green carbon energy and hydrogen are requiring guarantees of purchase, and the steel industry wants guarantees of supply at the right price. So that's a big issue. Decoupling of iron and steel making is, I think, going to happen. So ore with iron making and the renewable energy and steel making. In the meantime, we need to heavily tax the black steel, the non-compliant nations, to force them into looking at greening their situation. And we need to look at the best available technology for the brownfield sites that we currently are operating. So the green steel revolution spawned innovation and new technologies, but the question remains, can we innovate to market quickly enough? Can we actually use CCUs to fix the problem we're going to have for steel ultimately? And whether we can produce hydrogen efficiently and the costs can be improved significantly. And really, there's a huge opportunity for careers in the industry, especially for those willing to think outside the box that have had little industry experience and aren't, let's say, blinkered in the way of doing things of old. So with that, I will turn it back to you. Thank you for the opportunity. And if anyone has any questions, I'd be pleased to answer them.
Thank you, Sarah. Yeah. Any questions to Sarah?
This is a chart that I was mentioning about the steel that's changed in the industry. So there's quite a lot of information there, and it's all now coded
Yeah,
as to how.
Jushu, please.
I'm sorry?
No, Jushu has a question, I think.
Hi, Sarah.
Okay.
Thank you. Hi, Sarah, can you hear me?
Yeah, I can now. Yes.
Okay, thank you
Can't
so
see
much
you,
for
but
the
I can hear you.
for the wonderful talk. I think this is the talk, the first talk I have seen with so much probably complete data information and about the topic. So that's the questions I wanted to ask your view. I know you still pay quite a lot of attention about the UK steel industry. I think you know UK steel industry is going to switch to scrap-based EAF, but we do need probably, I would guess, around 1.5 million ton per year of OBMs. From your point of view, do you think it makes sense to build a HDRI plant in the UK, or is it better to source from outside?
Good question. From what I understand, the DRI plant people, well, the two majors, Tenova and Midrex, are now looking at building 2.5 million ton a year plants, period. They don't want to go smaller. They don't want to do demos, except the one that's going in with hybrid. Depend on your ore supply, power cost. I mean, you've got a huge issue with power costs in England. And I guess my question also to you would be, how are you going to make steel with the power costs the way they are? Will the government truly assist and lower the power costs for you? Because if not, you're not going to be competitive going to the EAF steelmaking route. In terms of I've not looked at the economics, but my gut's telling me I'd put a DRI plant somewhere in England and I'd sell the excess over the plant capacity that you require and make a profit that way to help pay for it. And you'd have control over your own, you'd have control of your own iron sources that way. Other than having to buy ore from offshore, probably.
Yeah. Okay. Yeah, I think I don't know the answer. I guess in the UK side, we're not us as the steel industry or the steel community is examining which way is better. I guess that's something needed to concede. And also, you mentioned a good point. It's about if we're running a scrap based or completely based on EAF, the economic sense is things to concede. Maybe we would like to invite you to give another talk to the UK steel community about how to make profit to run through running EAF production. I think that's probably quite useful, important topic for the UK steel industry.
Yeah, as you know, I was hoping to come over in March and talk to the industry and talk to different universities, but it turned out my US passport was within the 6 months and I really wasn't sure I would be allowed back in the country.
Okay.
But it really is a major topic, and I I heard the discussion in Parliament the other day where Alan was telling them that he'd been in the steel industry and for 25 years and they needed to listen to him. It was quite an interesting conversation. And yeah, I think that You know, it's sad to see that when I was in England, we were pretty good steelmaking community and could show the world, and now it's to the point where the question is going to be whether the steel industry in England continues or not. And there is a real issue with the economics of making steel the way you are currently, in terms of power and excuse me, in terms of the power. You've got the scrap. I mean, I know that there's over 10 million tons of scrap being exported that you can use internally. And you already know, you were involved with the work that was done on segregating and shredding and improving scrap, which will have a significant impact in terms of your efficiency, but the power is still the biggest cost that you're going to have.
Yeah.
For either hydrogen or for the furnaces themselves. I mean, it's a big number.
Yeah. Okay. So, Sarah, I think I will leave time for others to ask questions. One point from me is you're welcomed anytime when you are come to the UK, stop by and to visit our Steel Research Center and have another meeting. I don't know Claire is here or not. Claire is head of the group. I'm sure if she's here, she would express the same invitation to you.
Thank you. Well,
Yeah.
I should be in England before the end of the year.
Okay,
So
cool.
I will definitely take you up on that. Thank you.
Yeah. Yeah.
Thank you. Any other questions? Okay. If no more further questions, I would like to thank Sarah once again for the wonderful talk and for her time. And have a nice afternoon all. Thank you.
Thank you.
Bye-bye.
I will send you a copy of this, Prakash.
Yeah, thanks a lot. Thank you.
Thank you.
Okay.
Thank you,
Thank
Sarah.
Thank you. Have a great day. Have a good weekend.
Bye-bye.
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 Happy Easter.
Yeah,
You
you too. Bye-bye.
Bye-bye.